In previous lectures, we know that we have three types of passive elements. They are resistors, capacitors, and inductors. And in previous lectures, we already discussed resistors and capacitors. And in this lecture, we will introduce inductors. The inductor is typically a coil of conducting wires, and it stores energy in its magnetic field. The capacitor stores the energy in electric field, and the inductor stores energy in the magnetic field. And the resistor, it cannot store energy, it consumes energy. So they are different. Remember that for each element we discussed the relationship between voltage and current. For resistor, their relationship is Ohm's law, so that the voltage V equals I times R. For the capacitors, that is the current I equals the capacitance C times the derivative of voltage with respect to time. And for the inductor, so we have this relationship, that is the VL equals L is the inductance, times the derivative of the current with respect to time t. So this relationship tells us that this voltage is zero if there's no change in current. So if the IL is a constant value, the VL is zero. And if the current increase, the voltage VL will be a positive value. And if the current IL decrease, the voltage will be a negative value. And we can do the integration on both sides of this equation and obtain the equation for IL. So that is the integration to calculate IL. So this equation tells us that the inductance is a property whereby an inductor exhibits opposition to the change of the current flowing through it, measured in henries. Be careful that this is to the change of the current, not current. We know that the resistor R is opposed the flow of current, but the inductance is opposed the change of the current. So here we have a resistor VL, IL. So if the IL is increasing, so we can obtain a positive voltage, so that this voltage will oppose the increase of the current. If the current IL decrease, we will get a negative voltage, and this negative voltage, you can see that here, VL. This negative voltage will oppose the decrease of the current. So be careful that the inductance is a property oppose the change of the current, not the current itself. And the inductance of an inductor depends on its physical dimension and construction. There are some pictures of the inductors, and these are commonly used. They use the wires, and the inductance is proportional to the number of turns. So note that if the current is constant, then the inductance is 0. So the voltage drop is 0. The inductor acts as short circuit. So in DC steady state means that the current or voltage is not changing. So in this state, the inductor is equal to a short circuit. And in DC steady state, the capacitor will act as open circuit. So remember this conclusion. And also, since IT is differentiable, it must be continuous, so it cannot have abrupt change. Do you remember for capacitor, the voltage is continuous. Yeah, the difference is that for inductor, the current is continuous. For capacitor, the voltage is continuous. And we can calculate the current using this integration, and this IT0 is the initial current. Sometimes the initial current is 0, and sometimes the initial current is not 0. And we integrate the voltage on the inductor from T0 to T to calculate the I. And the energy stored in the inductor we can calculate using this equation. And here we assume that the initial current is 0. So, but do you remember the equation for capacitors? For capacitors is half times C times V squared. This is 1/2 times L times I squared. And if the initial current is not 0, we calculate the energy stored using this equation. So 2 conclusions you need to remember. The first one is that an inductor acts like a short circuit to DC. And the second conclusion is that the current through an inductor cannot change instantaneously. Let's take a look at an example. Here the current through a 0.1 Henry inductor. The current is given, and find the voltage across the inductor and the energy stored in it, so that we can use the equation that V equals L times di dt. So the L equals 0.1 and D, and we plug in the value for I, so that we can get so we can use the definition, the relationship between voltage and current, to calculate the voltage and the energy stored in it. So that is the energy stored times I squared. So use this equation, we can calculate the energy stored in it. The next example is to find the current through a 500 inductor if the voltage is this one, and also find the energy stored at T equals 5. So we can use the I equals and we plug in the numbers. The initial current is 0, so that we have 2t squared. So that when t find the current, so this is the current, right? And the energy stored at times 5, so that's the W equals times L times I squared when I is equal to 5. So that is the next one is consider the circuit and under DC conditions find the current I with the voltage VC and IL. And the second question is to find the energy stored in the capacitor and the inductor. So remember that in DC conditions, the capacitor is treated as open circuit. The inductor is treated as short circuit. So we can simplify this circuit so that we have a 12-volt voltage source, and so there's no current flowing through this 4 ohm resistor. So and this 1 ohm resistor and this 5 are in series. So the current I equals IL equals 2 ampere. And the voltage VC. So VC here is open circuit, so we plot the equivalent circuit. This is 1 ohm. So this is VC. So VC equals the voltage on the 5 ohm resistor. So that the VC equals 5 times I equals 10 volt. And the energy stored in the capacitor and inductor, WC equals VC squared. So this is 50. And the stored in the inductor is then we introduce the series and parallel of inductors. It's similar to the series and parallel of resistors. When the resistors are in series, we add them together, and when the inductors are in series, we add them together, and when the inductors are in parallel, we have this equation. So it's similar to the resistors in parallel. And we will not introduce how to derive this relationship, just remember the conclusion. This is a parallel. So let's take a look at an example. So to obtain the equivalent inductance of this circuit, we know that this 20, 12, 10 are in series, so that 20 plus 12 plus 10 equals 42, and then this 42 is in parallel with this 7 in parallel with 42 equals 6, so that the becomes like this one, 4 6 8, the LEQ, so that these 3 inductors are in series. So LEQ equals 4 plus 6 plus 8 equals 18 Henry. Yeah, that's